you with some experimental results how it compares with other frameworks. So about the language, this is probabilistic constraint logic theories are a probabilistic extension of constraint logic theories, which in turn are sets of integrity constraints, which have this form. Body implies head, where the body is a conjunction of atoms, and the head is a disjunction of atoms. And these integrity constraints can be complemented by a normal logic program called background knowledge, which provides application-specific, domain-specific knowledge. The semantics of these constraint logic theories defines the satisfaction of theory by a first-order interpretation. And the definition is very simple. If the interpretation together with the background knowledge is such that when the body of a constraint is true, then one of the disjuncts in the head is true, then the constraint is satisfied and the theory is satisfied if all the constraints are satisfied. So it's basically first order satisfaction. For these constraint logic theories, there has been proposed a learning algorithm called inductive constraint logic, which learns CLTs from interpretations, which scales well. And what we do in this work is to extend the language with probabilities. We make this constraint probabilistic based on the distribution semantics, and we provide learning algorithms for these probabilistic extensions of constraint logic theories. For our purposes, we extended the syntax of integrity constraints a bit because we use them in business process analysis, and this extension is useful for expressivity reasons. So we can, the syntax of our integrity constraint is a conjunction of atoms in the body implies a disjunction in the head, where the disjuncts can be either a positive or a negative literal, and the positive literals are implicitly existentially quantified, and the negative literals are implicitly universally quantified. And a theory is a set of these constraints, and each one is annotated with a probability from 0 to 1, of course. The semantics is given in the style of the distribution semantics. So PCLT, a theory, a probabilistic theory, defines a probability distribution over deterministic theories. You can get a probability distribution by taking each constraint, each ground constraint in the set of integrity constraints with probability equal to its annotation. So in this way, you have a number of possible theories, and in each of them, each constraint will either be present or absent. Each theory has a probability which is given by the probability of the annotation of the constraint that are in the theory multiplied by the product of the probabilities of the constraints that have been excluded complement to 1. So in this way, we have a number of possible theories, and each theory has a probability. Now, it's possible to give the probability of an interpretation by just summing up the probabilities of the theories that satisfy the interpretation. So you have a number of theories, some will satisfy the interpretation, some will not. If you sum the probability of the ones that satisfy the interpretation, you have the probability of the interpretation. It's like the distribution semantics, but of probabilistic logic programming. But in this case, we compute the probability of a whole interpretation and not just one atom. Okay, so let's see a very simple example where we have only one constraint. This is taken from the Bongard scenarios. And the theory is composed of only one constraint. In the predicates in the domain are triangle, square, in and inside. Triangle means that an individual is a triangle, of course, and so on. Inside means directly inside. One figure is directly inside one another, and in is the transitive closure of inside. So what the constraint C1 says is that a triangle cannot be in a square, because if we have a triangle T, a square S, and T is inside S, then the constraint, the body of the constraint is true and the head is false. So the constraint is not satisfied. But this constraint is probabilistic, has a probability annotation applied to it, which is 0.4. So in the first figure, we can see that the body of C1 is made true by the substitution 2 for T and 1 for S. So if we take, we can see that the triangle 2 is inside the square 1. And this violates the constraint. But since the constraint has probability 0.4, there is still a 0.6 probability that the theory is still satisfied by this interpretation. So this interpretation's probability is 0.6. Oops. In the second case, we have 3 possible substitutions. We have triangles 5, 3, and 4, which are inside the square 0. So in this case, we have 3 groundings of the constraint that are not satisfied. So we have to take the theories that contain none of these ground constraints, and the probability is 0.6 to the third, which is 0.216. So the probability of this interpretation would be 0.216. So this is the language and the semantics. To summarize, we have probabilistic integrity constraints with a distribution semantics. Now to the contribution, to the main contribution of this work, which is learning algorithms for this kind of theories. We learn from interpretations, so we start from a bunch of interpretations, positive and negative examples. So the first task that we tackle is parameter learning. Given a theory, a number of positive interpretations, a number of negative interpretations, and a normal logic program which serves as a background knowledge, we want to find the parameters, so the probability annotations in the theory that maximize the likelihood of the positive and negative interpretation. So in the paper, you can see that if you unfold the derivative of the likelihood, it doesn't admit a closed form solution. So we apply optimization. We experimented with gradient descent or a limited memory BFGS, and we found that gradient descent performs better. Gives better performance. We also do structure learning, so we start from a set of positive and negative interpretations and the background knowledge and a language bias, which is a specification of what the predicates can look like. And we try to find a theory that maximizes the likelihood of the positive and negative interpretation. So we want to find the theory that fits the interpretations best. And the search space is huge, of course. There are many possible theories. So our algorithm is greedy, and it works in 2 steps. First, it identifies a set of good candidate integrity constraints, and then within that set of integrity constraint, it builds the theory. And again, we during the search, we try to we optimize for the log likelihood. So the first phase is the search in the space of integrity constraint. It's a greedy search, so we start from a it's a beam search where we start from a single integrity constraint through implies false with the minimum possible log likelihood, and we apply we build new integrity constraint by applying refinement operators, which can for example, add a literal to the body or a disjunct to the head or other transformations of this kind. And we score each integrity constraint by applying parameter learning, like I mentioned before, on the theory, which is only composed of that integrity constraint.
So you have 2 minutes left, sorry.
2 minutes, okay, I'll be very fast. And in this way, we identify a set of possible integrity constraints. And in that set, we apply a greedy search for the best possible theory by basically starting from a empty theory and adding or removing each integrity constraint and seeing if it increases or decreases the likelihood. If it increases the likelihood, we keep it, otherwise we drop it. And of course, there are a number of parameters that we can use to fine-tune the algorithm, and this is the main algorithm that I summarized in the 2 previous slides. I won't go into it. So about experimental results, we compare Pascal, our algorithm, with some PLP algorithms, so lift cover, slip cover, and the relational classifier tilde. And we found that in terms of the area below the precision recall curve, it performs competitively. I mean, it's the best on 3 of the data sets we tested. It's the second best in 3 more, and so on. So it doesn't outperform the other algorithms, but in some scenarios it performs better. And for the area between the rock curve, the results are similar. We also compared it with Markov logic network algorithms, and still we found that the results are comparable. It's sometimes better, sometimes not. So the conclusion for our experimentations is that Pascal performs better on data sets that have a relatively small number of examples, but a big number of predicates. So it exploits its expressive language bias. And these are the conclusions. I don't know if I have a few seconds. I can't hear you, sorry.
I have to skip the question, but to finish your slides.
Okay, so we extended constraint logic theories to a probabilistic setting, and we proposed an algorithm for parameter and structure learning. And the experimental results are, in our opinion, promising. And what we plan to do now is to apply this algorithm to process mining and to the probabilistic verifications of business processes. And this ends the presentation. Thank you so much.
Thanks a lot, Marco.